So I was saying from the last tutorial, that is this is the instruction cycle. So the CPU goes from one state to another continuously, described as the instruction cycle. So this is the instruction cycle of the 6805 SoC. So it goes from one state to another, goes from reset 1, you can see it goes from reset to reset 1 to reset 2 to fetch, to decode, to execute, alt, BR bit, branch, line by line, and so on and so forth. Then within the circuit there were a few places that had an exception. The places where I wrote asterisk OP, you see it, some very few places asterisk OP. I didn't give a value there, I just wrote asterisk OP. It means that the value there is dependent on the value of what is the opcode, the operation code at that particular point in time. And the opcode is an 8-bit data. So you know, in normal SoCs or a normal computer, you have the opcode is more like the fetched data, the processing, so how the data affects the ROM. So that was why I gave another Excel sheet to show you what those values will be. Take for instance the fetch state. Okay, fetch state AC control has it, fetch state CC control has it, and fetch state AX control has it. So this is what the second Excel sheet looks like. This is the second one. So remember, this is the first one, which is the main instruction cycle. Now this second sheet here, I will explain to you how it works. Fetch state. So let me forget the thing is somehow not there. Okay, wait. Okay, I think it's okay now. So as I was saying, now this is more like a truth table, and this is the opcode, and these are the values it can be from 0 till 11111, because it's an 8-bit address. From 0 till I was getting this very well. I just want to explain this second Excel sheet. Now this is now the new values of the AC control, the new values of all these control signals, which are dependent on the opcode at a given state. This is for the first state. Remember, you can see that some are left empty. The ones that are left empty are the ones that already have a value in the main instruction sheet here. Take for instance here, you won't see SP control because the SP control and these ones already have a value. So the second table will only contain values for these ones and these ones that are dependent on the opcode. So you come here. So the value of the opcode determines the output value, but they are all in the same state, first state. We are talking about the first state. So assuming now we're in the first state and the opcode is 1000. Now this is the new value of the AC, new value of each of them. The same thing, if his opcode is 110, these are the new values. If opcode is 1001, these are the new values. Then it didn't only occur there, there were other states that had it. You can see here in the execute state also, they were dependent on the opcode. Then there was another state also here, also in the DIL state. You can see them here also. So whenever you see the asterisk OP, you can come down here and check the actual value. Now this is the second state that had it, the decode state. Now these are the different values of OP, and you can see now that here is actually empty because the opcode didn't affect this particular one, so it only affects the program control and the next state. So now depending on the value of the OP, when the state is when we're in decode state, so assuming the OP is 101, now the PC will be increment PC, and the next state will be the DIR state. So I think I've explained how this Excel sheet works, and that is what we call described as the instruction cycle. The instruction cycle completes when the CPU goes from the reset state number 1 down to state number right state, and when it gets down here it starts afresh again depending on the next value. So, and the opcode also determines too what state will be coming next. So then also you will see where they have this asterisk hierarchy here. This one was a special case, it didn't appear much, so I made a separate circuit for it. So that one, this is the circuit I made for that hierarchy. If you go through the file code, you definitely understand how it works. So there were some control signals that had only one ROM and some that had 2 ROMs. Now something like this opcode control has only one ROM. It means that it was never affected by the opcode. The AC control has 2 ROMs. The first ROM is the normal instruction cycle ROM, and the next ROM following it is the opcode ROM. Whenever it's affected from the opcode, that is the Excel sheet number 2. So take for instance this CC control. The data in this ROM here are data from the main instruction cycle, whereas this second ROM here are data from the Excel sheet number 2. So for those who use registers, I'll just preview it so you see what the content looks like. Here is what the content looks like. I think if you need more explanation on it, you can maybe send me a chat. Then it's very easy, but it might look confusing at first. Take for instance, let me explain one of this ROM, and remember this is how the next state. Let me explain again the next state and the previous state. This is the next state here, this is the current state. So after this current state here, the next state is the state coming into through the register become the current state. So the next state is the previous one that is waiting to come out, and you can see where this state here holds this line. This particular line is a very long signal, so that is where the rest of the ROM comes from. You can see that's where all of them come from. So that line is the line that tells them the current state we are. And you know how ROM works. ROM and RAM, they need an address. So once they're on that line, they get the address of the current state. Then they give the actual data at that state. So that is why you see here that the current state actually is what generated this particular signal line here. It goes up and down for all the signal ROM to tap from it. So it taps from them and reads and pushes out the particular value of the control signal, and that value is what will now determine, will now control the multiplexer, which determines what the register will have as an output. I explained what the registers does and how the control signals are being manipulated, so I don't think there is much I will explain there too. So remember, the left side are for generating the control signals, this right side are the actual one, and the control signals, they all come from a ROM. These ones are in a register, these ones are in the different separate ROMs, and the value in the ROM comes from this Excel sheets. Is also on the website, the two of them. So what I did is just to pick them column by column and save them in a ROM. So whatever the state has determines what it will give as an output. So I think that would be all about this. So this is what makes up the 42 instruction cycles for the ROM. For the CPU, these are the 42 instructions. You can see here that it stops here 43 or 42 because of the number one has already gone out with the heading. So if not, they actually 42 in number. So all these values you are seeing here, they've all been explained on the website, so I don't want to start explaining them again. These are all of them. So they correspond to a value of a control signal. So I don't know, I'm thinking of what else to explain here. We have the bset and bclear ROM. You see it on the code. This is the VMA and the read write bit. They go together with the address. So let me explain more further, just very few more. Let's talk about the let's talk about the this address. Now let me show you how you understand this. Let me go to the website, then let me find the address register, and this is the address register, and it's being controlled by this signal address control. You can see how the wire went here. It controls the read write, the VMA, then the address itself, and it's a 3-bit signal. Now whenever it is 00, it means reset the address. When held in reset, sets ADR to OXFFFF, and that is hexadecimal. It sets the ADR to FFFF. Now you can see that 00, this is the value in 00, FFF. So it sets the CPU address to address FFFF, and what has that address FFF is actually the ROM. That is at initial setting, when everything is 00, the CPU is reading from the ROM, not this ROM. There's another subcircuit ROM. So these ROMs are the program ROM. They store ROM data. They store data for the program. I also have a separate ROM subcircuit. So that's where it's feeding the first data from. When this address is FFF, that is 111. Now the next value for it is when it's 001, it means vector low address. Fetch interrupt vector low. Now let's go there and see. And this is the second one here. And let me highlight the signal. One, it went to this splitter, and from this splitter it went here. Now follow the highlight signal to see where it comes from. Now you can see it's coming from here. This is the interrupt vector register, and that is what is saying here. Fetch the interrupt vector low. Then again, the next one says when it's 01, it says fetch address, fetch opcode from PC. Now let's see what it does. which is this next one here. Let me highlight it and see where the data is coming from. Now let's go up and see where it's coming from. It says fetch opcode from PC. Now you can see it's coming from the program counter. Then the next one says read address, read from memory. The next one for is means write to memory. So let's see this read and write from hand to memory, what it does. So I will highlight it. I've highlighted it. It's reading from where the memory, and is reading from this effective address is a memory storage of the address register. That's what it said. Read from memory, write to memory. So then again, they have the next one, push and pull from start. Then before that, you find out that this read and write from memory, this is what it looks like there. Where is it? I'm no longer in the ear. Can see this is what it looks like. Two of the inputs. The first one, the up one is read, the next one is write. So but they are all reading and writing from the memory. So the data is coming from the EAR register memory. But how does it determine whether it's reading or writing? Is the value here. So whenever it's in read mode, this comes on. So whenever this one is on, that is this read write bit, it starts reading. Whenever is off, it starts writing. So that is how this particular section works. Then again, let's go through the, now you can also see it from the code itself. But when you're talking about the write address, the address is still the EA address, that is EA memory. And when you're talking of reading, the address is still the EA address, but the difference between them is this bit here. Now here the read write is 0, while here the read write is 1. But the VMA, the valid memory address, is always 1. It indicates that yes, it's actually writing or reading from a valid memory. So the code also, we explain the circuit too for you. So you can go to the code. If you use the Velo code combined with the circuit, you understand it more. The same. So they are all multiplexers controlling each of the registers. All multiplexers, all of them are multiplexers. These are all the control. This ALU control, IV control. Now this ALU control is the actual ALU bit, the ALU control. Now let me show you what this ALU control bit does. Let's go to the CPU tab. Let's go here. Now I will highlight it so you see. Let me highlight the ALU control so you see where it goes to. Sorry. I'll follow it and watch. So this is where it goes. So depending on what value it is, it determines which of the ALU output you are going to have. I already explained this when I was treating the ALU control. Let's open the ALU map so you see exactly what it does. So this is it here. That ALU control bit comes here and choose which of these ALU operations to perform. So that one is what does this job of choosing. It does this job of choosing what the ALU is going to perform at a particular instant of time. I think that is all for the CPU register. Use the code and you understand how the multiplexers are able to make the decision of choosing which bit to work with. So I had a method I did, but okay, there's no time, I won't be able to explain it. How I was able to fill up the ROM. So now let me briefly talk about it. This is what you see here. This is the readable part, but for you to fill a ROM, you don't write latch EA fetch MD latch PC to the ROM. You either add a binary data, that is, if you are doing it practically, you are going to add binary data to it. In Logisim, I added hexadecimal data to it. So this is what the sheet looks like initially. So for people who want to have something related to, if you want to be able to write instruction cycle, you'll be able to do something like this. Now this is where it comes from. Sorry. So I had a small Python code that took the words and turned it to letters for me. So this is what they actually look like in Python. I just turned those binary data to letters. So 00 means reset state, 001 means reset 1. If you need the Python code, I can send you. So it's very a simple code. It just swaps between letters and binary figures. Then I now have another code which I use to convert the binary to hexadecimal, because what Logisim needs is hexadecimal data for their ROM before I was able to fix them into their ROM. So what I did was I actually gave each of them a particular value. Now this is for the address control bit. These are the values there. This one is for the stack SP control bit. This one is for the CC control bit. So I just gave them a unique value. When it's pull CC is 100, when it's load CC is 010, when it's latch CC is 110, when it's set CC is 000. The same. Now this is for all the LEO control, all the LEO operations. Give them a particular value. So this for the state. All the states have their unique binary values. The first state, you can see it is 0011, the code state 0000100. So that is how I was able to transcribe between these cells. So this is what they look like earlier. From here I took each of them column by column, converted them to hexadecimal before sending them to Logisim to put into the ROM. I took them column by column. So I did another one wonderful thing so assuming they have 2 bits, something like the AC has the AC control is 2 signal. So the first 2 are the actual signal. Now the last one, if it's 0, it means it's not affected by the opcode. But if it's 1, it means it has an opcode data. So you can see the same thing here. All this one where the last letters are 1 are the ones that has this asterisk, that has this OP asterisk to it. So I just figured a way to arrange the instruction cycle together. But if you go through the site, this is what it looks like. It was more like a state machine on the website. It was more like a state machine on the website. So I think this is where I will end this tutorial. Maybe I will continue again to explain it better.